I have my favorite theorems in measure theory, Lebesgue integration, as many people do. Fatous Lemma's on the list, as is some other theorems, like I like Agarov's theorem and some other ones that come to mind, but Fatous Lemma is really at one of the top of the list, and it's a very simple theorem, lemma. And what it says is that if I have a sequence of measurable functions, then the limit inferior, the lim inf of fn of x over r, d mu, I forgot my little d mu here, is less than or equal to the limit inferior of the integral over r of fn of x. So pulling the limit out, you don't get equality, and in fact there's examples where you don't get equality, but it gives you this nice inequality, and it seems so innocuous. But a lot of times we have integrals with sequence of functions, especially in partial differential equations. We want to prove something about a function, which all we know about it is that we can express it as a limit of a sequence of functions that are nice. And we want to pull up nice property through for this limit, for this that we know holds for the sequence of functions. We want to pull it through to the actual limit of the functions, which you usually can't do easily. Fatous Lemma doesn't give you equality, but it allows you to bound below in some way, you're bound above in some way your function, which you want to prove something about, which is this lim inf of the fn, with a sequence that you know is nice. So it's actually pretty important in the terms of PDEs. We do use it. I can actually prove this. It's one thing I can prove for you. I'm not going to prove everything because I skipped too much measure theory to be able to do that. But just to remind you what the lim inf is, you take the sequence of functions fn of x and you fix n equals 1. You look at the entire sequence and you find the infimum of that set. Call it whatever it is. It has an infimum. Then you set n equal to 2, and you look at f2 to on to infinity. That's set, and you find the inf of that set, and you'll get a different number, and for fixed x, and so forth. So I keep chopping down, raising my n, and I find the infimum. And this way, all these infimums create a sequence, and this sequence converges, and it converges to what we know as the lim inf. If I choose my n big enough, then the inf of that set starting at n is going to be equal to the lim inf eventually, right? You're going to eventually throw out all the outliers, and you're going to get to a point where the infimum stays solid because you have an infinite sequence. So let capital N be fixed so in that way, and then in that case the lim inf and the inf are one and the same things. But the infimum of that sequence is always going to be smaller than any member of that sequence by definition of infimum. So for each little n, I'm going to have that property. Since this inequality holds for each of the little n's, then it's going to hold for the infimum of these little n's. Little topology coming in here. So the infimum's always going to be no worse than the lim inf. So I can cap this above by the lim inf of this sequence of integrals. And so therefore I have the property that the lim inf of fn is going to be less than or equal to the lim inf pulled out. Very slick, very easy. And that's pretty much all I will be able to prove for you without having more measure theory background. I do want to mention what does almost everywhere mean, AE, because we use it quite a bit. It means that the property, if I'm talking about a property holding almost everywhere, it holds everywhere except on a set of measure 0. So for example, it's used often about functions. The functions can equal each other almost everywhere. or a result, a property, or a theorem can hold almost everywhere.